First, we discuss about a little bit about the introduction to my research. And the second one is the objective of my study. And the third one is an in-depth discussion of result and finding about my research, and that can be divided into a three major sections that we will discuss more into detail later. And the fourth one is the overall conclusion. And finally, the last one is some recommendation for future study. So at the moment, with the decreasing availability of fossil fuel and awareness of a human impact on the environment, so we have to seek an alternative from renewable energy sources such as biomass to generate available chemical for various types of application. And one of the main component in biomass is lignin that has become popular to produce a green and bio-based material and products. And lignin has a high potential as a chemical derivative. So in plant, lignin acts by providing a structural integrity to the cell wall. It also protects from the microbial attack and also act as energy storage. And there are three types of lignin. First, we have H-lignin or hydroxyl phenylpropane. Then we have a guaiacyllignin or G-lignin. And then we have S-lignin or syringil. And within the chemical structure of lignin, there are four chemical functional groups, namely hydroxyl. We have a hydroxyl, we have a carboxylic, we have a carbonyl, and we have a methoxyl group. And due to the complex three-dimensional complex nature of lignin structure, it has remained as one of the most difficult biopolymer to characterize. So both lignin and cellulose, it exists in biomass, and such as a bamboo, for example. So, for example, we have a figure of biscuit here. This is a good analogy if you want to represent lignin and cellulose. In the middle, dekat tengah-tengah tu, we have a cream, right? So this is the analogy for lignin. It binds together the cellulose and the biscuit together. And if you want to utilize this material, if you want to utilize lignin, we need to first separate it into a lignin-rich stream and cellulose or sugar-rich stream. And we can make a lot of things from a sugar-rich stream. For example, we can make ethanol and other platform chemical. And for lignin, we pretty much burn it to get energy. But recently, there comes a lot of groundbreaking. Banyak research yang dibuat sekarang tentang lignin, on the utilization of lignin. But why? Why suddenly we have a lot of groundbreaking research on lignin? Because the more we utilize the cellulose from biomass, the more lignin we end up with. And to make this process more economical and sustainable, we need to make use of lignin in an efficient way. And it is such a way if we don't utilize lignin properly, since it is the most energy dense molecule in the whole lignocellulosic material. So here we have a lignin microstructure. As we can see from the figure here, it is very complex and dense molecule. So let's break it down to several molecules. For cellulose, if we break it down, we will get a cellulose. But if we break down lignin here, we have a dense macromolecule of lignin here. If we break down it, we can get up to a few hundred molecules. And then we can use bacteria here. We feed them this compound and funnel them to a very few intermediate from which we can get a lot of product such as aromatic product, for example, miconate, fatty acid, and lipid. So petroleum is the key aspect of the chemical industry. It is the raw material for a basic chemical, and we mainly use it to produce various types of product. And the growing demand in dwindling resources, meaning that the chemical industry is increasingly focusing on renewable resources. And we have a lignin as one of the main components in biomass. That is a very promising resources. It is currently almost exclusively used to generate energy, although it can be used for many other types of application. And here we have a global scheme of lignin utilization. So we can utilize lignin either without lignin either without a chemical modification and also with chemical modification. And among the potential uses of lignin we can use it for energy production. Lignin is used as a carbon source for production of energy. And we can also use it as micromolecules, a micromolecular nature of lignin. We applied it to the area of a wood binder or adhesive, like what I will explain later. Polymers such as polyurethane form and also a carbon fiber. And also we can use lignin for aromatic that use the technology to cleave the lignin structure into a monomer without the aromatic ring being eliminated to produce a polymer building block. Aromatic monomers such as benzene, toluene, ethylene, phenol, and also vanillin. So if we look at here, we can see that lignin has a lot of application. We can use it for concrete dispersion, for fine chemicals, for fuel, carbon product, energy storage, thermoplastic, rubber reinforcement, and many more. So in industries such as the paper industry and other related products, chemical pulping, we conduct it to remove lignin in order to obtain the valuable cellulose fiber, like what we can see in the figure here. So this figure shows the schematic concept of a biorefinery of lignocellulosic biomass, where we apply a pretreatment to separate lignocellulosic materials into each distinct component, such as cellulose, lignin, and hemicellulose. So lignin is always considered as a waste product, and we use it mainly as a source of a cheap fuel in mill. Although in biomass, lignin consists of 30% of all non-fossil organic compound on Earth, we only utilize a small number. So only a small number has been commercialized for formulation of surfactant, dispersant of adhesive, antioxidant in rubber and polymer industry. So from here we can see that the extraction of or isolation of lignin from a cellulosic material, we can perform it by physical, chemical, or combination of both physical and chemical method, and also through a biochemical method. And lignin structure and properties are highly dependent. Dia sangat bergantung kepada what types of process that we choose, and also to its botanical source. So maybe we have a lignin from bamboo. Maybe its structure is quite different from a lignin from other source such as contoh macam daripada tebu ataupun daripada palm oil. The properties in terms of structure may be different. So from here we can see the method of delignification. It can be divided into sulfur process and a sulfur-free process. In sulfur process, we have a sulfide and kraft, and we will get a lignosulfonate lignin. And here we have a kraft lignin. And in a sulfur-free process, we have a solvent pulping and a soda pulping. And from here we get an organosolved lignin, and from a soda pulping we have a soda lignin. So utilization of lignin without further modification would be favorable, although modification of lignin is not compulsory. It is always a requirement before its utilization as a starting material for a polymer and a chemical synthesis. So a direct application of lignin in industry is possible, although only a limited number of a small amount, only a small amount as a result of a thermal degradability, mechanical properties, and reactivity. So the chemical modification of lignin, we can classify it as a fragmentation or the polymerization of lignin into aromatic monomer, and also creating a new chemical sites through modification, and also hydroxyl group chemical modification. So this is the figure that I show you how we can apply lignin as a phenol replacement in a phenol-formaldehyde resin. Here we have a G-type lignin, via lignin, and a phenol here. We can see the chemical structure is almost similar. And from the equation here, we can see that lignin could also react with a formaldehyde. HCOH is a formaldehyde, and could be cross-linked with a formaldehyde the similar way as a lignin, as a phenol formaldehyde condensation reaction. And so here the three position of G lignin type. You can see here the G lignin, it has a three position, gave this significant value compared to syringyl type lignin, which have both a 3 and 5 position attached to the methoxyl group. And this group, it will prevent the occurrence of a polymerization reaction, or what we call as a steric hindrance, especially in chemistry. So this is the significance of my study. First, I want to increase the technical data and encourage more effective utilization of bamboo as a source of biomass. And this study will give a better understanding on the lignin chemical structure and thermal behavior. And the third one is the environmental and economical point of view. It is advantageous if we want to implement lignin as a partial replacement in a PF adhesive. So here is the objective of my study. First is want to determine the psychochemical characteristic in four Malaysian bamboo variant. And the second one is to isolate lignin from Malaysian bamboo and characterize its chemical and thermal properties. The third one is to synthesize and develop lignin-phenol-formaldehyde adhesive and determine the properties of the adhesive in terms of chemical, thermal behavior, and physical properties. And finally, to characterize the mechanical strength of the adhesive by tensile lab shear strength. So here in the first part of my study, I studied the psychochemical characterization of four Malaysian bamboo type. So I studied the properties of bulu beting, bulu semantan, bulu lemang, and bulu akar. So from the figure here, it shows the experimental design for the first part of my study. And from the table here, I will not go through into the detail of this table. That this indicate the instrument used for analysis and characterization. So this is the result of a psychochemical properties of bamboo biomass. So other properties of bamboo studied were specific gravity, the pH, and extractive content as tabulated here in the figure. And from the result, we can see that there are only a slight difference between the various types of bamboo, and the specific gravity of bamboo are considered very high, ranging from a 0.7 to 0.85, and the pH value for all bamboo species falls within the slightly acidic region from 4.3 to 5.33, and for alkaline extractive content or alkaline soluble, the average value was within 24.36 to 25.63. And finally, for ethanol toluene extractive content, the average value for all the bamboo species was within the range of 4.1 to 7.21%, whereas for the hot water extractive content, the results range within 10.5% to 12.7%. Spectroscopic analysis was also carried out using FTIR analysis, whereas the crystallinity was determined using XRD analysis. And from here, we can see the IR spectrum within the fingerprint region is shown here. From the result, it can be concluded that all types of bamboo has a high degree of similarity in terms of a chemical structure and also a functional group that exists. And from the spectrum, we can observe that the semantan bamboo ataupun bulu semantan has the highest intensity of OH group compared to other types of bamboo. And here, this figure shows the XRD pattern of a bamboo fiber and the existence of a two diffraction angle indicated here, semi-crystalline, indicated that the bamboo fiber is semi-crystalline with the crystallinity index between equivalent to 42 to 44.4%. So XRD result, it can give us information about the crystallinity, the crystal size, and the degree of crystallization. And this is a very important characteristic as they are closely related to the fiber strength, properties, elongation, modulus, and also at the density of the bamboo fiber. So I also determined the ash content, calorific value, and elemental composition of a bamboo ash. And from here, we can see the average ash content of bamboo was equivalent to 5.91%. For semantan, 5.43 for beting bamboo, 8.5% for lemang, and 5.85% for bulu akar. And the results of a calorific value was within 17 megajoule per kilogram to 18.05 megajoule per kilogram for all the bamboo species. And from the table here, it indicated the elemental composition. From the table here, from the figure here, it indicated the elemental composition of a bamboo ash in a milligram per kilogram. And from the data, we can see that the principal ash forming element in bamboo ash are potassium, K, calcium, magnesium, and silica. Why I perform all this analysis? Because the calorific value is the key parameter when we want to evaluate the quality of a biomass for energy application. And here we have the experimental design for the second part of my study. And within this section, I studied the thermal characterization, chemical structure, microstructural and ash content of bamboo lignin. And from the figure here, it shows the method of isolation using a soda pulping method. I use sodium hydroxide. Why I choose sodium hydroxide? Because it extensively degrades the bond between the lignin and carbohydrate, and thus making it easier to dissolve lignin with less degradation and oxidation of a lignin molecule. And before that, I perform a pre-treatment of a bamboo fiber using a hot water extraction in autoclave. So here we have a structural analysis of lignin carried out using NMR analysis. And from here, we can see the peaks and its corresponding assignments are tabulated in the table. And here we can conclude that the relative content of a syringeal and a guaiacil unit in different types of bamboo is almost identical. And this is a proof that the highest similarity in terms of a chemical structure among all types of a bamboo lignin. And here we have the microstructure analysis of lignin at a 3000 times magnification. So here we can see that all the lignin specimen, they exhibit a little bit difference in microstructure compared to other bamboo lignin. Uh, the lignin that we get from a cementan bamboo here, SL is a lignin that we obtain from a cementan bamboo. It has a rough surface with the existence of a visible pore. And this rough surface, they are very quite important because they are beneficial because it can promote dispersion and penetration into lignin during the adhesive synthesis. And then we have a thermal analysis of lignin carried out by using thermal gravimetric analysis and differential scanning calorimetry. So from here we can conclude that the range of TG, or glass transition temperature, for all bamboo lignin is quite small, and this is expected since all the bamboo undergo the same treatment method, that is soda pulping method. And this indicate that all the bamboo has almost similar molecular weight, and the lower glass transition temperature that we observe here, it is very beneficial because it gives a more free volume and increase the possibility of a cross-linking formation during the synthesis of Lignin-Phenol-Formaldehyde. And I also conducted X-ray analysis of bamboo lignin, and we can see the result here in the figure. And from here we can conclude that there is no indication of intense peak at 22.1 degree in all lignin sample. And this indicate that the cellulose are non-existent in all lignin sample that we obtain from bamboo. And we can say that the soda pulping that we choose have been effectively separate lignin from cellulosic biomass. And here we have a ash content analysis of a bamboo lignin. So ash content can be attributed or due to the pulping process where the sodium hydroxide was used. And from the analysis, I observed that the ash content of bamboo lignin range from 7.14%, the highest, to 0.91% at the lowest value. And here we now we are in the third part of my study where I develop and characterize Lignin-Phenol-Formaldehyde. And this is the experimental design for the third part of my study. So the lignin substitution was conducted from 0% up to 20% as tabulated here. And here we have the flow of how lignin was obtained from a biomass. We obtain a black liquor from bamboo, and then we got a precipitated lignin cake, and then we have a dried lignin, and subsequently we use dried lignin as a replacement of a phenol in the synthesis of phenol-formaldehyde adhesive to produce lignin-phenol-formaldehyde adhesive. And I also produce a PF adhesive without lignin substitution, just to compare the properties as a control, just to compare the properties of a PF adhesive without lignin and lignin-phenol-formaldehyde adhesive. And here is the result of a gelation time of adhesive. Gelation time analysis of adhesive was also carried out. We can define a gelation time as time required for liquid adhesive to change appearance into gel that is no longer workable. And here we can see as the lignin ratio becomes higher, the gelation time decreased by 64.3% for BLPF from lignin-phenol-formaldehyde that I synthesized using lignin from a budding bamboo, and 63% reduction in gelation time for SLPF, using a lignin that I obtained from Semantan bamboo. And here we can conclude that the faster cross-linking rate is due to the result of interaction between lignin and phenol to form a lignin-phenol-formaldehyde condensate. And here we have the results of a FTIR analysis of adhesive for both control and both lignin-phenol-formaldehyde within the fingerprint region. So what we can conclude here is that there is a high degree of resemblance between the control and the lignin-phenol-formaldehyde adhesive. And also we have XRD analysis, XRD diffraction analysis carried out to determine if there are any changes in adhesive when lignin was used as a partial replacement for phenol. And surprisingly, it was found that there is only a slight reduction in the crystallinity when lignin was added into the system. And from the figure here, we can see the scanning electron microscopy to study the effect of lignin on the adhesive. So the surface of cured adhesive was studied using SEM. And from here, we can conclude that the QPF has a generally smooth surface. And this is a very good indication of a high reactivity between the phenol and the formaldehyde. And here we have a thermal analysis of lignin. So in this section, the thermal analysis of LPF was also evaluated. And from here, we have a figure of a TGA analysis and DSC analysis. So TGA, if you still remember, it gives the information of the weight loss of material in relation to temperature degradation, and increase in lignin content, as we can see here, lowered the thermal resistance and reduced carbon residue at elevated temperature. And both lignin that I obtained from both bamboo species that I utilized to synthesize lignin-phenol-formaldehyde adhesive, both exhibit a good thermal resistivity with a carbon residue of more than 50% at 800 degrees Celsius. And here we have a differential scanning calorimetry analysis. I use it to determine the curing temperature of the adhesive. It is one of the most important parameters to ensure that the pressure curing of the adhesive in press, but also to determine the quality of adhesion in the final engineering wood product. So here we can conclude that the incorporation of lignin for up to 20% has led to the increase in the peak and end set temperature as a result of the complexity of a lignin-phenol-formaldehyde adhesive compared to the pure phenol-formaldehyde or control adhesive. And now the last part of my study, I also performed the mechanical characterization of adhesive, lab shear adhesive dry strength. I carried out the analysis based on the British standard 1204. So the lab shear strength or the lab shear strength tests are commonly used if you want to determine or characterize the bond strength of adhesive, and each measure the strength of an adhesive on a specific substrate. So the area of a shear equivalent to 2.5 centimeter and 2 times 2 centimeter, and the substrate is a wood material. And then I carried out the shear strength of the adhesive using UTM or Instone machine. And here we have the result of the bonding performance of lignin-phenol-formaldehyde. So the analysis of a tensile lab shear dry strength indicated that for both lignin-phenol-formaldehyde formulated with a partial replacement using both type of bamboo, adhesive formulation with 15% here. Bila kita ganti phenol at the ratio of 15% for both types of lignin, for both types of adhesive synthesized using lignin from 2 different sources of bamboo. So the adhesive formulation with a 15% replacement give the highest lab shear strength. And this shows that the high prospect of lignin that obtained from bamboo as a partial replacement for a phenol formaldehyde, as a partial replacement for phenol in the synthesis of phenol formaldehyde adhesive. So here are the overall conclusion that I conclude from my study. So here we just focus on the lignin utilization in the synthesis of adhesive. So we can see that from the result, the gelation time analysis revealed that the lignin effectively accelerates the curing rate of adhesive, and both PF and LPF has a high similarity in terms of a functional group, and as further indicated by the FTIR and NMR analysis, and the curing temperature of adhesive, as we can see from the result beforehand, decrease as the amount of lignin within the system increase, and the lignin replacement at 15%, it gives us the highest lab shear strength, and all the LPF adhesive gave a satisfactory result that surpassing the relevant international standard. And here are some recommendation for future study. Maybe if you are interested in the utilization of lignin as an adhesive, maybe you can look at this recommendation. Maybe for future study, we can use other lignin modifications such as methylolation and phenolation should be carried out. In my study, I did not perform any lignin modification. I just used the lignin as is from the bamboo. And comparison between the non-modified lignin and modified lignin should also be conducted in terms of chemical structure and thermal characteristic. And if we want to yield more accurate result from the lab shear strength, we should employ ABS or automated bonding evaluation system to prepare the sample. And this is very important, the last recommendation for future study. I think formaldehyde emission of adhesive should also be evaluated in the future. I think that's all for my presentation. Thank you for listening. So if you have any question, boleh tanya.
Doktor,
Yeah.
bamboo ni dia guna nak buat adhesive tu kan?
Yeah, betul.
Apa application dia? Application.
Adhesive tu. Application dia dalam kalau phenol formaldehyde ni, we utilize it in a wood industry untuk industri kayu. Untuk kita nak produce glue lamp, kita nak produce wood engineered product lah.
Okay.
Sekarang kita pakai phenol formaldehyde. Tapi masalahnya phenol formaldehyde ni dia produce a lot of formaldehyde emission. Dia bahaya lah. So kita nak replacekan phenol dalam phenol formaldehyde tu sedikit pada kita pakai lignin. Faham
Faham. Terima kasih.
So yang lain ada soalan? Last week Dr. Ivy present pasal apa ya?
Yang hydrogen
Hydrogen technology.
hydrogen.
Oh, hydrogen technology. Okay. So any more question before we end our session today?
Doktor, dia ada any disadvantage tak?
Apa dia?
LPF ni dia ada any disadvantage tak?
Kalau yang daripada segi disadvantage tu, mungkin cara kita nak treat lignin tu supaya dia lebih reaktif dengan formaldehyde. Mungkin kalau kita nak treat lignin tu mungkin menggunakan chemical. So bila kita apply chemical, so cost akan meningkat lah. Itu salah satu disadvantage lah bila kita nak apply lignin sebagai pengganti kepada phenol dalam lignin dalam adhesive.
Oh, okay, thank you doktor.
So any more question? So siapa yang buat FYP dengan saya, buat tajuk macam ni lah lebih kurang. Kita akan study lignin, not only from bamboo, also from other types of biomass, macam kelapa sawit. Daripada bulu tu salah satu source lah. Ya, rasanya saya sampai sini je lah ya. Nanti saya akan share rakaman dengan you all. Okay, thank you again. Thank you for listening.
Thank you, Doktor.
Thank you, Doktor.
Bagus lah ya.
Thank you, Doktor.
Thank you, Doktor.